Okay, so we are calculating this P0. So uh, what's done is to take the first order derivative of that P0 and then obtain the value for P0, and that's your MLE. And if it turns out that the best value for P0 is giving you uh, P0 estimate lot smaller than 0, then it doesn't mean anything to have a power that is smaller than 0. So you will just end up using P0 is equal to 0. That's better than having P0 estimate less than 0. Okay, so this is in accordance with the parameter constraint. Okay, so if to put it this way, then the MLE is P0 equal to max 0 this, or if it turns out this item gives you negative values, then at least you can use 0. That's what max is doing for you. Okay, and this is reasonable since this is equal to that. So we will let uh, P0 have plus equal to this, where the plus subscript is meant to remind us P0 plus head is the MLE, it is positive. The GLRT The GLRT decides H1 if this is larger than a threshold. Okay, so P0 is MLE is obtained and you put it in, and X condition on non P0 and non hypothesis, you can write it out. And likelihood ratio, take the log, which is monotonic, and then go through the likelihood ratio test, and then it becomes Ln Lg equal to this and this and that. Some of those terms come from the new denominator. Then using 8.6, this is Ln equal to this. 8.6 is 8.6 is this J of P0 here. So you put it inside this term and then do some simplifications, and then eventually you get to the point of you have this, so you have lambda, and we call that lambda is the equal equal thing, right? When it is equal, that makes it possible. If it's unequal, then we will not be able to have this solution. Okay, so doing step-by-step simplification, eventually we get to the point. Now if P0 is 0, and then Ln will be 0. Since this is larger than 0, then we choose H0. Then that's consistent with our intuition. On the other hand, if this is larger than 0, then P0 is P0 hat, P0 plus. Then this is, but the function, then that Ln Lg simplified from all the way to here, all the way. P0 plus, um, P0 plus is the notation for it's the MLE, it's the MLE if the whole thing is positive. If the whole thing is positive, then we call it P0 plus. Okay, but the function is a monotonic increasing function of x for x larger than 1. And the probability function which is defined for this. So it's to plot this out. And this is what this is this. Right? This is this. So a part of this function which is defined for x larger than 1 is shown in 8.1. 8.1 function required for this GLRT. And that's the inverse, its inverse exists. And upon letting this, we decide H1 if that is the, okay. So I think that is reasonable, right? if you have this n divided by 2 and this function larger than a threshold, because that g function is monotonic increasing, so it's equivalent to you want to threshold a g function and things larger than something, uh, it's monotonic increasing with x. Therefore, you are thresholding this is equivalent to thresholding its argument p0 lambda over sigma square. And doing some interchange, you get this p0 larger than gamma. Okay, so but with some intuitions and derivations, finally we will decide h1 if this is larger than gamma prime. So what that means is this is almost close to the uh, energy detector, right? The energy detector that we have before, Okay, so it eventually get to the point of this formula. And then the next one is the unknown signal power, the low rank covariance measure. Another special case of interest occurs when the signal covariance matrix is low rank, as already discussed. So if, for example, lambda 1 not equal to 0, but lambda I equal to 0 for I larger than 1, then CS is this is reduced to lambda 1, because if you see it, this will be like P0, right? Eventually it will be plus P0 multiplied by lambda 2, V2, V2, T, and so on and so forth. But because lambda 2 and afterwards are all 0, so this thing goes to 0, and only that term remains. So this is a rank 1 matrix. This arises from a DC level in which Sn is equal to this, and it's distributed by Gaussian distribution. So in this case, CS is sigma A 1 transpose, so that the remaining eigenvalues are 0. Okay, and then for the rank 1 covariance matrix, by minimizing this, we want to minimize this and all the thing, and it comes from 8.5. So if we plug this thing into 8.5, right, 8.5 over here, you plug it in, then you have this J, and then differentiating and set to 0, you get P0. And as long as larger than 1, then it's given us like something like P0 plus thing that we had before. So it's either 0 or this one. Okay? And then, yeah, P0 plus. And then GLRT becomes like this, and taking log, which I will skip some details. So eventually you go to a point where you get something like this. And by the same argument as before, we have t of x equal to this. So some of the calculation details are skipped, but I think it's fine. You have this eigenvectors with the collected data and square, which is kind of similar to energy detector, except that it's weighted by its eigenvectors. So from a DC label problem, so that you have V1 equal to that. So T of x is equal to this, and then you put that in, you put this into there. So we decide H1 if this x squared, x bar square larger than something, but eventually it will be just a threshold, right? So it doesn't matter if you do this division by n or not. It doesn't matter that much. Okay. Okay. So I think that's good enough for us. So just to summarize the GLRT for the general problem. Okay, just to summarize, you have a CS theta, and theta is a vector, and GLRT decides H1 if this is a summary. Okay, just a summary. Likelihood ratio larger than the threshold. So taking some logs and simplifications, you get the point. And then later on, you get this, and then uh, at the same time, when you get H1, you also get the MLE, which is the theta hat as a MLE that's put into the likelihood ratio. Okay, so we will stop right here, and I think for chapter A, we will just go up to here. And yeah, thank you.